In the icy vacuum of space, 13 billion light-years from Earth, something beyond the stars stares back at us. The James Webb Space Telescope has penetrated the cosmic abyss deeper than any instrument before it, and what it has discovered defies all the laws of physics as we understood them. Ancient galaxies that shouldn't exist, black holes older than time itself, and signals from wandering worlds screaming through the void. If you enjoy uncovering the universe's darkest secrets, hit the like button, because what I'm about to show you will forever change your perception of reality. Brace yourself. Here we go. Something is terribly wrong with the universe itself. For decades, scientists thought they understood how quickly our cosmos was expanding. The Hubble Space Telescope has given us one dimension. Mathematical models predicted otherwise. Everything seemed to fit together into a single cosmic puzzle. Then the James Webb probe peered deeper than anyone had ever looked before, and the puzzle exploded into 1,000 pieces. The universe is expanding at two completely different rates, depending on where you measure. Imagine it like an inflating balloon. Only the top half is expanding twice as fast as the bottom. This should be impossible. The laws of physics demand that expansion occur uniformly throughout space. Webb confirmed what astronomers feared most. When they measured the expansion rate using distant stars called Cepheids, they arrived at a single number. When they calculated it using the cosmic microwave background, they got a completely different number. The difference is not small. We're talking about a discrepancy so colossal that it suggests our fundamental understanding of reality is flawed. Scientists call it the Hubble tension. But that name doesn't convey the true horror of what we're dealing with. This isn't just a measurement error or a calibration issue. After studying more than 1,000 Cepheids in 5 separate galaxies stretching 130 million light-years into space, the discrepancy remains. The implications are staggering. Either our models of how the universe works are completely shattered, or there's some unknown force tearing reality apart. Dark energy, the mysterious substance driving cosmic expansion, may behave in ways we never imagined. Some regions of space may be expanding faster than others, creating cosmic rifts that call everything we know about space-time into question. Adam Reyes, the lead researcher who discovered this crisis, put it bluntly. When measurement errors are ruled out, there remains the real and exciting possibility that we have fundamentally misunderstood the universe. The word exciting seems inappropriate given what this means. If our basic understanding of cosmic expansion is wrong, then all our calculations about the age, size, and ultimate fate of the universe are in question. Webb's unprecedented precision has removed any doubt about the measurements. Both the telescope and Hubble are capturing the same impossible contradiction. The universe is expanding, but it's doing so in a way that violates the laws of physics as we understand them. This discovery alone would be enough to shatter cosmology textbooks. But Webb was just getting started. As the telescope continued its survey of deep space, it began to find objects that shouldn't exist, behavior that defies explanation, and phenomena that suggest our reality is far stranger and more dangerous than we ever imagined. The expansion crisis was just the beginning of a series of discoveries that will force scientists to question everything they thought they knew about the cosmos. But what Webb discovered next seems trivial in comparison. 6 impossible monsters are drifting through ancient space and rewriting the laws of galactic evolution. When the James Webb Space Telescope trained its infrared eyes on a seemingly empty patch of sky near Ursa Major, astronomers expected to find tiny infant galaxies struggling through their first billion years of existence. Instead, they discovered 6 massive, mature star systems that shouldn't have had time to grow so much. These galactic giants contain almost as many stars as our own Milky Way, yet they formed when the universe was just 3% of its current age. Imagine trying to grow a full-sized oak tree in 3 months. That's essentially what these galaxies have achieved on a cosmic scale. Star formation takes time. Gravity requires millions of years to gather enough gas and dust to trigger thermonuclear fusion. Yet these 6 systems somehow accelerated their development, becoming galactic titans while the universe was still in its cosmic infancy. The discovery occurred almost by accident. Astrophysicist Erica Nelson was examining postage stamp-sized sections of Webb deep field images when she noticed several hazy red dots that seemed impossibly bright. Red light in astronomy typically denotes old light, stretched by the expansion of the universe during its long journey to Earth. But these objects were both ancient and blindingly bright, a combination that defied explanation. Each of these monster galaxies contains between 10 billion and 100 billion stars. To reach such enormous sizes so quickly, they would have to form hundreds of new stars every year for hundreds of millions of years. Our Milky Way, by comparison, creates only about 2 new stars annually. These ancient systems were stellar factories, operating at a rate considered impossible by modern physics. The team has informally nicknamed these objects interrupters of the universe, because they threaten to disrupt our understanding of how cosmic structure forms. According to all the scientists' simulations and models, matter in the early universe must have slowly and methodically condensed. Small structures would have gradually merged to form larger ones over billions of years. These 6 galaxies throw this entire timeline out the window. They suggest that the early universe was capable of organization and complexity cosmologists never thought possible. Either there exists a completely unknown mechanism for the rapid formation of galaxies, or our fundamental assumptions about cosmic evolution are catastrophically flawed. The discovery raises daunting questions about the role of dark matter in early cosmic development. If galaxies could grow so massive and so quickly, it means dark matter condensed and attracted ordinary matter at a rate far exceeding current predictions. The invisible framework that shapes our universe may be far more turbulent and unpredictable than we realized. Joel Lee, one of the astronomers studying these objects, captured the scale of the problem perfectly. "We've peered into the very early universe for the first time and found something so unexpected that it creates real problems for science. But confirming whether these are real galaxies will require further observations with the Webb spectrograph. And what these subsequent studies have revealed is even more alarming than anyone expected. A monster with the mass of 50 million suns is wandering the cosmos, all alone, and it's rewriting cosmic history." Deep in the early universe, the James Webb spacecraft discovered something that shouldn't exist according to all theories of black hole formation. Cuson is a supermassive black hole, virtually without a surrounding galaxy. It's essentially naked, drifting through space without the usual swarm of billions of stars that typically accompanies such massive objects. Most supermassive black holes reside at the centers of galaxies, like cosmic anchors surrounded by rotating disks of stars, gas, and dust. They form symbiotic relationships with their galactic hosts, growing together over billions of years through a delicate dance of gravity and star formation. Cuson defies all these rules. This cosmic wanderer contains a mass equal to 50 million of our suns, compressed into a space smaller than our solar system. To put this into perspective, if Earth were the size of a marble, Cuson would still be invisible to the naked eye, but it would contain more matter than exists in hundreds of billions of ordinary stars. What makes this discovery truly alarming is the timing. Cuson exists in the infancy of the universe, just 600 million years after the Big Bang. Traditional black hole formation requires the death of massive stars, which means waiting for the first generation of stars to form, their lives, and spectacular supernova explosions. This process should take much longer than 600 million years. Roberto Mielino, the Cambridge astrophysicist who helped identify Cuson, called the find completely out of the ordinary. The object challenges all existing models of how supermassive black holes grow and evolve in the early universe. 3 theories attempt to explain Cuson's existence, each more troubling than the last. The first proposes that some black holes form directly from the collapse of massive gas clouds, bypassing the stellar phase entirely. The second proposes that intermediate-mass black holes somehow grew at an impossible rate, consuming matter faster than physics would allow. The third theory is the most troubling of all. Cuson may be a primordial black hole, created in the first seconds of the universe during the violent fluctuations of space and time immediately after the Big Bang. If so, it means Cuson has been lurking in the cosmic darkness since the very beginning, waiting 13 billion years for stars and galaxies to form and illuminate its presence. Cuson is one of hundreds of such objects identified by Webb. These tiny red dots appear throughout the early universe. Each one is a potential cosmic monster, defying explanation. They glow with the light of matter being torn apart and superheated as it spirals into their gravitational vortexes. The existence of these naked black holes suggests that the early universe was far more chaotic and turbulent than cosmologists ever imagined. Instead of the gradual, orderly formation of cosmic structures, we may be seeing evidence of primordial catastrophes that gave birth to massive black holes even before the first stars existed. If Cuson is indeed a primordial black hole, it represents something far more ancient and alien than any galaxy or star. But Cuson wasn't the only impossible black hole Webb discovered lurking in the cosmic depths. Black holes older than the first stars illuminate the universe, and they may have been there since the moment of creation. Scientists have long suspected that supermassive black holes formed after the first generation of massive stars collapsed in spectacular deaths. This process should take hundreds of millions of years. As gravity slowly gathers enough matter to trigger thermonuclear fusion, the stars live short but vibrant lives and then explode as supernovas, leaving behind stellar remnants. But the James Webb Space Telescope has discovered evidence of supermassive black holes when the universe was only 400 million years old, far too early for this traditional formation process. Andrea Ferrara and his team at the Scuola Normale Superiore in Pisa, Italy, propose a radical solution to this cosmic conundrum. What if black holes, not stars, were the first significant sources of light in the universe? What if primordial black holes, formed in the chaotic first seconds after the Big Bang, were already lurking in the darkness, when the universe was still in its infancy? These hypothetical primordial black holes would have formed through a completely different mechanism than stellar black holes. Instead of collapsing stars, they arose from extreme density fluctuations in the primordial soup that existed less than 5 seconds after the Big Bang. Imagine the early universe as a turbulent cauldron of energy and matter, where some regions became so dense that they collapsed directly into black holes, never forming stars. It's like observing a cosmic avalanche so powerful that it creates its own gravitational trap. This direct collapse mechanism could explain one of Webb's most puzzling discoveries in the early universe. The telescope has discovered supermassive black holes that are far too massive for their age, reaching enormous sizes faster than conventional formation models allow. If black holes can form directly from collapsing gas clouds, they could reach supermassive status much faster than previously thought possible. The Infinity Galaxy provides a real-time laboratory for studying this exotic formation process. The black hole appears to be actively feeding on gas flowing between the two galactic cores, growing in size as the collision continues. Radio-accelerated observations reveal intense emissions of energy from the precise location of the black hole, confirming that it is actively consuming matter. But the most troubling aspect of the Infinity Galaxy collision isn't what we can see happening now. It's what this discovery suggests about the violent processes that shaped the early universe. If the direct formation of black holes through collapse was common in the cosmos's youth, it means the universe went through a phase of incredible violence and chaos that we are only beginning to understand. And this cruelty has left behind objects even stranger than wandering black holes. Hundreds of orphan worlds drift through space in pairs, broadcasting radio signals that shouldn't exist. The James Webb spacecraft has identified more than 500 free-floating planets in the Orion Nebula that don't orbit a single star. These cosmic wanderers, each roughly the size of Jupiter, were ejected from their parent star systems and now drift into the cold void of interstellar space. What makes them truly strange is that many of them travel in pairs, orbiting each other at distances ranging from 25 to 400 times greater than the distance between Earth and the Sun. Scientists call these paired wanderers Jupiter mass objects in binaries, or JMBs. They challenge all theories of planet formation we've developed. Planets typically form in disks of gas and dust surrounding young stars, slowly accumulating material until they reach their final size. The gravitational dance required to create binary planets should be incredibly rare. Yet, Webb has detected dozens of such cosmic pairs. The mystery deepened when astronomers pointed radio telescopes at these binary planets and discovered something unprecedented. Several JMBs emit radio signals with patterns never before observed from planets. These aren't the typical emissions you'd expect from worlds with magnetic fields interacting with charged particles. They produce radio bursts at gigahertz frequencies, thousands of times higher than FM radio signals. On Earth, radio signals at these frequencies come from technological sources or extremely energetic astronomical phenomena, such as pulsars and quasars. Their detection from rogue planets suggests that these worlds are undergoing physical processes not found anywhere else in our solar system. The radio emission appears to be related to the binary nature of these planets. When two massive objects orbit each other, they create complex gravitational interactions that can generate powerful magnetic fields and electric currents. Think of it as cosmic friction on a scale never before encountered. JMBs are essentially gigantic electrical generators, powered by their orbital dance. But the signals themselves remain deeply mysterious. Different pairs of JMBs produce distinct radio signatures, suggesting that each binary system has its own unique electromagnetic identity. Some emit constant streams of radio waves, while others produce sporadic bursts that defy any discernible pattern. The implications are troubling. If these abandoned worlds can generate such powerful radio signals, what else could they be capable of? Their magnetic fields could be orders of magnitude stronger than anything we observe in our solar system, triggering cosmic phenomena capable of influencing neighboring star systems. Even more troubling, the existence of so many giant planets suggests the formation of planetary systems. If hundreds of such paired worlds exist in just one nebulous cloud, there could be millions or billions of them throughout our galaxy. Each represents a failed solar system, a cosmic tragedy where gravitational interactions went awry and planets were ejected into eternal darkness. These wandering worlds are cosmic orphans, forever separated from the warmth and energy of their stellar companions. They exist in perpetual darkness, drawing warmth only from the slow decay of radioactive elements within their cores and the tidal forces generated by their orbital dance with their companion. But as alarming as these rogue planets were, Webb discovered worlds that challenge our understanding of planet formation in an even more fundamental way. A subsequent discovery forced scientists to rethink everything they knew about planet formation around young stars. A young star system violates the basic rules of planet formation, creating worlds from the wrong materials. In a star-forming region known as NGC 6357, James Webb discovered a planet-forming disk, nearly devoid of water but rich in carbon dioxide, precisely where Earth-like planets should form. This discovery shatters one of the most fundamental assumptions about how rocky planets form around young stars. Every model of planet formation predicts that the regions around young stars where rocky planets form should be saturated with water, ice, and silicate minerals. Water is one of the most abundant molecules in the universe, and its presence in planetary disks is considered essential for the formation of life-supporting worlds. The disk around the star XU10 throws these assumptions into disarray. When Webb studied this system with its near-infrared spectrograph, astronomers expected to see the familiar signatures of water vapor mixed with other common compounds. Instead, they discovered a disk dominated by carbon dioxide in the inner regions, where Earth-like planets typically form. Water is so scarce that it's barely detectable, creating an environment unlike any previously modeled by scientists. This discovery challenges everything we understand about the chemistry of planet formation. On Earth, water played a crucial role in shaping our planet's geology, atmosphere, and, ultimately, the conditions that allowed life to emerge. A planet forming in the XU10 system would develop under completely different chemical conditions, potentially creating types of worlds unparalleled in our solar system. Two theories attempt to explain this strange chemistry, and both have troubling implications. The first suggests that intense ultraviolet radiation, either from the young star itself or from massive nearby stars, effectively sterilized the disk, splitting water molecules and carrying away hydrogen, leaving oxygen to combine with carbon. The second theory is even more disturbing. The dominance of carbon dioxide may be the result of unusual conditions in the dust grains that make up the planetary disk. Instead of being coated in icy water, like dust grains in normal systems, these particles may be coated in carbon dioxide due to the unique environmental conditions around this young star. Either explanation suggests that planet formation may follow paths astronomers never imagined. If ultraviolet radiation can strip water from planet-forming disks, this means that many potentially habitable worlds may never acquire the necessary chemical building blocks to support life. The galaxy may be filled with dry, carbon dioxide-rich planets, formed in conditions hostile to the chemistry we associate with life. This discovery also raises questions about the diversity of planetary systems across the galaxy. If planet formation can lead to such dramatically different chemical environments, then entire classes of worlds may exist that operate through geological and atmospheric processes we have never encountered. The XU10 system represents a natural laboratory for studying alternative pathways to planet formation. As the planets in this system evolve, they will provide insight into how worlds form, when the primary chemical ingredients are fundamentally different from those found in our own solar system. But the strange chemistry of planet formation was only one of many atmospheric mysteries uncovered by Webb. The telescope's next target would reveal a world so hostile and alien that it challenges our definition of what constitutes a planetary atmosphere. A world so close to its star that its surface glows, like molten metal, somehow maintains an atmosphere that defies all laws of planetary science. 55 Cancri orbits its star so closely that a full year passes in just 18 Earth hours. This hellish planet is tidally locked, meaning the same side always faces the star, creating a day side hot enough to melt copper and a night side immersed in perpetual darkness. Surface temperatures reach over 2,200 degrees Celsius, hot enough to vaporize most known materials. By all the laws of planetary physics, this world should have lost its atmosphere billions of years ago. The James Webb spacecraft discovered the impossible. This hellish planet not only has an atmosphere, but is composed of materials that shouldn't exist as gases at such extreme temperatures. The atmosphere appears to be rich in carbon monoxide and carbon dioxide, forming a dense blanket around a world that should be as airless as Mercury. The discovery was made through careful temperature measurements with Webb's mid-infrared instrument. When astronomers measured the thermal radiation from the planet's day side, they found it was colder than expected. Something was blocking and redistributing the star's heat, and that something could only be an atmosphere thick enough to transfer energy from the scorching day side to the frozen night side. This atmospheric circulation creates one of the most extreme weather systems ever discovered. Imagine winds howling at thousands of miles per hour, transporting vaporized rock and metal from the day side to the night side, where these materials condense and fall as rain of molten minerals. The temperature difference between the day side and night side must exceed 1,600 degrees. But the atmosphere somehow moderates this difference through convective currents operating under conditions no laboratory on Earth could replicate. What makes this atmosphere truly impossible is its source. The hellish planet's atmosphere cannot be a remnant of its formation, as solar winds from the nearby star would have stripped away any primordial gases over millions of years. Instead, researchers believe it is a secondary atmosphere, constantly escaping from the planet's interior. Imagine a world where the crust itself boils. Intense heat and tidal forces from the nearby star literally cook the planet's interior, causing carbonaceous materials deep underground to evaporate and escape through volcanic outgassing. The atmosphere is continually stripped away by stellar radiation and continually replenished by geological processes operating at temperatures that would vaporize most known materials. This creates a hellish cycle in which the planet's own interior fuels its impossible atmosphere. Rock vapors rise from the surface, are carried across the planet by supersonic winds, condense on the night side, and return as liquid metal and rock. The entire world has become a massive distillation apparatus, operating under conditions that push the boundaries of physics. The existence of an atmosphere on 55 Cancri E suggests that planets can retain gases in far more extreme conditions than scientists previously thought. This has profound implications for our understanding of potentially habitable worlds. If atmospheres can survive such hellish conditions, they may also persist on planets we've previously written off as too hostile for any form of atmospheric chemistry. But the impossible atmosphere of the hellish planet was merely a warm-up for Webb's next discovery. The telescope was about to encounter a visitor from another star system that would challenge our understanding of time itself. An ancient comet from another star system is hurtling through our solar system. And it's older than Earth, the Sun, and everything we call home. Comet 3 I Atlas seems unremarkable at first glance. About 7 miles wide, composed of ice and rock, it's on a trajectory that will take it past our Sun before returning to the void between the stars. But detailed analysis of James Webb revealed something that shouldn't have been possible. This interstellar visitor is approximately 7 billion years old, making it 3 billion years older than our entire solar system. When astronomers tracked the comet's steep trajectory through space, they realized it originated from the flat disk of the Milky Way, a region of our galaxy filled with ancient stars that formed when the universe was much younger. This cosmic wanderer drifted through interstellar space before the Sun was even a glimmer in its stellar nursery. It predates Earth, Mars, Jupiter, and every planet in our neighborhood. Webb's near-infrared spectrograph revealed that the comet's coma, the cloud of gas and dust surrounding its nucleus, is composed primarily of carbon dioxide, rather than the water vapor typical of comets in our solar system. This unusual composition provides clues about the chemical environment of the star system in which it formed billions of years ago. The comet is traveling at over 210,000 miles per hour, fast enough to cross the entire United States in less than 2 minutes. Its trajectory is unusually flat and straight, unlike anything else in our solar system. This interstellar interloper follows galactic gravitational rules rather than the Sun's, viewing our entire solar system as just another obstacle to navigate. What makes this ancient visitor truly unsettling is what it represents. Tri-I Atlas is a messenger from a time when the universe was radically different from today. 7 billion years ago, the Milky Way was more chaotic and turbulent. Star formation rates were higher, heavy elements were scarcer, and the chemical processes that form planets operated under different conditions. This comet formed around a star that lived and died billions of years before our Sun formed. It survived the death of its parent star, perhaps the violent supernova explosion that destroyed its original solar system and sent it wandering the galaxy. For 3 billion years, it traveled through the cosmic depths, a frozen time capsule carrying the chemical traces of an ancient era. The fact that we can see it now raises troubling questions about how many other ancient visitors might be passing through our solar system undetected. Tri-Atlas is only the third confirmed interstellar object ever discovered, but statistical models suggest that tens or hundreds of such cosmic time travelers should be traversing our environment at any given moment. Each one represents a fragment of a shattered world, a piece of cosmic history that survived catastrophes we can barely imagine. They are archaeological artifacts of star systems that existed when the universe was young, carrying information about galactic conditions from eras that no other objects can provide. But the Tri-Atlas also serves as a reminder of the ultimate fate of our solar system. In a few billion years, when our sun begins to die, objects from our world may be ejected into interstellar space, becoming ancient wanderers that will puzzle astronomers in distant galaxies long after Earth is gone. The visit of an ancient comet was a harbinger of cosmic timescales beyond human comprehension. But Webb surveys have revealed objects even more mysterious than ancient visitors from dead star systems. 300 mysterious objects glow in the early universe, and astronomers can't figure out what they are. Deep surveys by the James Webb Space Telescope have discovered a new population of cosmic objects that don't fit into any known category. These small red dots appear as tiny crimson sparks of light scattered across images of the early universe. But their properties are so unusual that scientists struggle to classify them. Each one is far brighter than it should be, given our knowledge of how galaxies and stars formed in the universe's youth. The mystery begins with their color. In astronomy, red light typically indicates either great distance or low temperature. These objects are certainly distant, existing when the universe was less than 1 billion years old. But they are also incredibly luminous. They produce enormous amounts of energy through unknown processes, creating a combination of properties that is unlike any object in the modern universe. Using advanced techniques such as infrared imaging and spectral energy distribution analysis, astronomers from the University of Missouri have identified 300 of these mysterious objects in Webb data. Each is roughly the size of early galaxies, but produces far more light than predicted by galaxy formation models. If these are galaxies, they are unlike any known to exist today. The objects are so bright that they are forcing scientists to reconsider how galaxies could have formed in the early universe. Traditional models suggest that the first galaxies grew slowly, accumulating matter through gravitational collapse over hundreds of millions of years. The small red dots suggest that some process created massive, luminous structures much faster than current theories allow. But here the mystery deepens. When astronomers try to pinpoint what exactly is producing all this light, the answers make no sense. Some of the objects appear point-like, suggesting they may be powered by supermassive black holes rather than by distributed star formation. Others show signs of extended structure, indicating that they may be true galaxies undergoing extremely rapid star formation. The most troubling possibility is that these objects represent a completely unknown phase of cosmic evolution. During the first billion years of the universe, physical conditions were completely different than today. Matter was denser, dark matter interactions were more frequent, and the cosmic web of large-scale structure was still forming. These conditions may have allowed the creation of types of objects that cannot exist in the modern universe. Some of the small red dots show signs of extremely high-energy processes. They emit X-rays, ultraviolet radiation, and infrared light in patterns that suggest violent, chaotic energy production. Whatever powers these objects operates under extreme conditions that push the boundaries of known physics. The objects also appear randomly distributed throughout space, rather than clustered in regions where early galaxy formation would be expected. This random distribution suggests that they may represent a fundamental property of the early universe, rather than rare, isolated phenomena. Bang Jangsun, a graduate student leading the study, emphasizes that even if only a few of these objects are confirmed in the early universe, They will force scientists to revise existing theories of galaxy formation. The sheer number of mysterious objects discovered by Webb suggests that our understanding of cosmic evolution in the early universe is fundamentally incomplete. The tiny red dots represent perhaps the most significant challenge to cosmology uncovered by Webb. But their mystery pales in comparison to what the telescope discovered when it peered into the large-scale structure of the universe itself. Galaxies across vast regions of space rotate in synchronized patterns, suggesting that the universe may have been born rotating. In what is perhaps the most stunning discovery of James Webb, astronomers have found evidence that galaxies separated by millions of light-years rotate in a coordinated manner. This cosmic choreography challenges our understanding of how structure forms in the universe and raises the possibility that the entire cosmos was born with a preferred rotation direction. The discovery arose from observations of 263 galaxies imaged by the Webb Deep Space Telescope. When astronomers analyzed the orientation and rotational patterns of these distant star systems, they discovered something that should have been impossible according to standard cosmological models. Galaxies too far apart to exert any gravitational influence rotate in the same directions. Imagine discovering that every windmill on an entire continent is spinning in the same direction. Despite the lack of a wind pattern to coordinate their motion, galaxies are separated by distances so vast that light from one would take millions of years to reach another. Yet, they are all engaged in the same cosmic dance. Leo Shamir, the computer scientist who led the analysis, identified two possible explanations for this phenomenon, both deeply troubling. The first is that the universe was born rotating. If the Big Bang itself had angular momentum, it could have imprinted a preferred direction of rotation on the cosmic structure that formed after it. This explanation is consistent with black hole cosmology, a theory that proposes that our entire observable universe may be the interior of a massive black hole within a larger parent universe. If so, the rotational patterns observed by Webb could be evidence of the parent black hole's rotation, transmitted on cosmic scales by mechanisms we don't understand. The second explanation is even more troubling for conventional cosmology. If the universe wasn't born rotating, then the coordinated rotations of galaxies suggest that existing theories of cosmic evolution are fundamentally incomplete. Some unknown force or field must act on scales greater than anything scientists have previously considered. The implications extend far beyond galaxy formation. A rotating universe would have different physical properties than the static cosmology described by standard models. Space and time themselves could have preferred directions, creating asymmetries in the laws of physics that could influence everything from particle physics to the ultimate fate of the universe. The discovery also raises questions about dark energy, the mysterious force driving cosmic expansion. If the universe has a preferred rotation axis, the effects of dark energy could vary depending on the direction, creating a cosmos that expands faster in some directions than in others. This could explain some of the anomalies detected by Webb in the rate of cosmic expansion. Perhaps most troubling is what a rotating universe implies about our place in the cosmic hierarchy. If our universe rotates within a larger structure, it implies that reality extends far beyond the limits of observable cosmology. We may live within just one component of an incomprehensibly vast multiverse, where entire universes rotate like galaxies within some multidimensional space. The coordinated rotations of galaxies pose a fundamental challenge to our understanding of the formation of cosmic structure and the nature of space itself. But the hidden rotations of the universe were only the beginning of Webb's assault on conventional physics. The James Webb Space Telescope's latest discovery has shed light on black hole formation, which occurs through processes seemingly impossible. A supermassive black hole is forming in real time through a mechanism that violates all the laws of stellar evolution. Deep in space, James Webb has discovered a collision of galaxies that has produced something extraordinary. The system, which astronomers call the Infinity Galaxy, contains a supermassive black hole that appears to have formed through direct gravitational collapse, rather than through the death of massive stars. This process is unfolding in a place where a black hole would seem out of place. A black hole lingers in a vast expanse of glowing hydrogen gas between two merging galaxy cores. In typical galaxy mergers, the supermassive black holes from each galaxy eventually converge, forming binary systems that either merge or eject one of the black holes entirely. The Infinity Galaxy defies this pattern, containing a black hole in a gravitational vacuum. Pieta Vanum and Gabriel Brahma discovered the system while studying deep Webb images. The galaxy's distinctive figure-8 shape immediately caught their attention, but subsequent observations revealed something far more significant. Radio emission from this system points to a massive black hole precisely where theory predicted it would not survive. The process of direct collapse acts like a cosmic avalanche. When two galaxies collided, gigantic streams of gas formed between their nuclei. Under precisely defined conditions, these gas streams became so massive and dense that they collapsed directly into a black hole, bypassing the star formation stage. This is gravitational collapse without the intermediate stage of stellar evolution. This discovery resolves one of Webb's most puzzling findings. The telescope discovered supermassive black holes in the early universe that are far too massive for their age. Traditional black hole formation requires waiting for massive stars to form, evolve, and die in supernova explosions. This process takes hundreds of millions of years, but Webb discovered mature supermassive black holes existing just 600 million years after the Big Bang. Direct collapse black holes can reach supermassive sizes much more quickly because they begin with a huge amount of material. Instead of starting as stellar mass black holes and growing through accretion, they form with masses potentially millions of times greater than our Sun. This head start allows them to become the monsters Webb observes in the early universe. The Infinity Galaxy provides a real-time laboratory for studying this exotic formation process. The black hole actively consumes gas flowing between colliding galactic nuclei, growing in size before astronomers' eyes. The system demonstrates that black hole formation can be much more dynamic and rapid than scientists previously assumed. However, the direct collapse mechanism raises troubling questions about the cosmic violence of the early universe. If such processes were common in the early universe, this means that galaxy formation was accompanied by catastrophic events that could have instantly created some of the most massive objects in the universe. This process also suggests that supermassive black holes may play a more fundamental role in cosmic structure than previously thought. Rather than forming as byproducts of galaxy evolution, they may be the primary drivers of matter organization on the largest scales. The direct collapse black hole in the Infinity Galaxy proves that the universe possesses mechanisms for creating massive objects that operate much faster and more violently than conventional models predict. But even this rapid black hole formation couldn't explain the most extreme matter consumption Webb was hoping to detect. The telescope's next target was a cosmic monster devouring matter at a rate that, according to the laws of physics, should be impossible. A black hole in the early universe is devouring matter 40 times faster than the laws of physics allow. And it's growing at an incredible rate. Hidden among thousands of X-ray sources in deep space, James Webb has identified a supermassive black hole that defies fundamental rules about how quickly these cosmic monsters can consume matter. The object, designated L1568, is devouring matter 40 times faster than its theoretical limit, challenging our understanding of black hole physics. Every black hole has what scientists call the Eddington limit, the maximum rate at which it can accrete matter without allowing the intense radiation pressure from superheated gas to disperse its food supply. Imagine trying to drink from a fire hose. Above a certain flow rate, the pressure becomes so intense that it prevents further consumption. L1568 somehow drinks from 40 fire hoses simultaneously. The discovery required a combination of Webb's infrared sensitivity and data from NASA's Chandra X-ray Observatory. L1568 was initially buried among thousands of bright X-ray sources, invisible to optical telescopes, but shining in high-energy radiation. Webb's unique infrared capabilities allowed astronomers to identify faint return emissions that revealed the object's true nature. What makes this black hole's feeding frenzy truly alarming is the implications of its growth rate. With such extreme accretion rates, L1568 could have accumulated most of its current mass in a single episode of rapid absorption. The black hole appears to be undergoing what astronomers call a feeding episode, consuming vast quantities of matter in a relatively short period of cosmic time. The object exists only 1.5 billion years after the Big Bang, when the universe was still in its infancy. For a black hole to reach supermassive status so quickly while adhering to normal feeding limits, it would have to start with incomprehensibly large initial masses. The extreme feeding rate of L1568 offers a potential solution to this cosmic timing problem. The speed and volume of material escaping the black hole suggest that significant portions of its mass growth occurred during similar feeding frenzies. These aren't gradual accretion processes spread out over billions of years, but rather violent consumption events that can increase the black hole's mass by enormous factors in a cosmic instant. The physics of such extreme consumption remains poorly understood. The black hole somehow stabilizes the accretion process, despite the radiation pressure that should disperse its food supply. Either the black hole has developed some mechanism to control the radiation pressure, or the surrounding matter has properties that allow it to resist dispersal. L1568 represents the extreme limit of black hole consumption behavior, operating under conditions that push physics to its limits. The discovery suggests that the early universe was the scene of gobble-up events far more violent and rapid than anything observed in the modern cosmos. These rapidly feeding phantoms could explain how supermassive black holes reached their enormous sizes so quickly in cosmic history. Instead of slowly, steadily growing over billions of years, they experience brief but intense gobble-up episodes that increase their masses by a factor of 10 or more. But the impossibility of L1568's gobble-up rate was just one example of the strange behavior Webb discovered in the early universe. The telescope's surveys revealed that the cosmos's youth was far more chaotic and violent than anyone had imagined. Massive galaxies lie dead and silent in regions of space where they should be blazing with star formation, and astronomers cannot explain why they have ceased growing. James Webb has discovered what researchers call sleeping beauties, galaxies scattered throughout the early universe. These massive star systems mysteriously cease star formation when they should have been at the peak of their activity. These cosmic giants contain billions of stars, but show no signs of creating new ones, contradicting all models of galaxy evolution in their youth. The discovery occurred when astronomers studied galaxies formed between 600 million and 6 billion years after the Big Bang. During this period, the universe was rich in gas and dark matter, creating ideal conditions for rapid star formation. Most galaxies of that era should have been ablaze with the light of newly formed stars, consuming available gas at a frantic rate to build their stellar populations. Instead, Webb discovered numerous massive galaxies that appeared to have entered a cosmic hibernation. These systems contain stellar masses comparable to the Milky Way, but show none of the vigorous star formation expected of young galaxies. They resemble massive cities where all construction has suddenly ceased for no apparent reason. The nickname, Sleeping Beauty, derives from their dormant state during what should have been their most active period. Like a fairy tale princess falling into an enchanted sleep, these galaxies stopped growing at the peak of their development. But unlike in a fairy tale, there's no obvious explanation for what triggered their cosmic hibernation. Several theories attempt to explain this strange behavior, each challenging fundamental assumptions about galaxy evolution. The first suggests that the supermassive black holes at the centers of these galaxies have become so active that their energetic output has heated the surrounding gas to temperatures too high for star formation. This process, called active galactic nucleus feedback, could shut down star formation throughout the galaxy. But the timing isn't right. Sleeping Beauty galaxies show signs of ceasing star formation even before their central black holes became active enough to cause such widespread heating. There must have been some other trigger for their hibernation. A second theory suggests that these galaxies used up their gas reserves so quickly during the initial burst of star formation that they literally ran out of fuel. This explanation requires star formation rates far exceeding those predicted by current models, suggesting that early galaxies were much more efficient at creating stars than modern systems. The most troubling possibility is that Sleeping Beauty galaxies encountered some unknown process that doesn't exist in the modern universe. The early cosmos operated under different physical conditions, with a higher matter density and a different distribution of dark matter. Perhaps these conditions allowed for mechanisms to halt star formation that we've never observed. The existence of sleeping galaxies in the early universe has profound implications for our understanding of cosmic evolution. If massive galaxies could halt their growth processes so early in cosmic history, it suggests that galaxy formation is far more complex and unpredictable than scientists previously thought. These cosmic sleeping beauties provide further evidence that the early universe was a far stranger and more violent place than our models predict. A rogue planet drifting through space has developed the strangest atmosphere ever discovered, with distinct cloud layers composed of iron and magnesium minerals. SIMP J0136 plus 0933 is unlike any world in our solar system. This cosmic wanderer does not orbit a star, but drifts freely through the galaxy, illuminated only by the dim glow of its own internal heat. Webb's detailed analysis of the atmosphere revealed something unprecedented. This rogue planet has a layered atmosphere, where iron rain falls through clouds of magnesium minerals. The planet's atmosphere resembles a cosmic layer cake, with various types of metallic clouds located at different altitudes. Near the surface, a dense layer of iron clouds creates weather conditions unlike anything on Earth. These are not thin wisps of water vapor, but dense accumulations of vaporized metal that condense and fall as liquid iron rain during the planet's storms. Higher in the atmosphere, a second cloud layer composed of forsterite, a magnesium-rich mineral often found in meteorites, creates an entirely different weather system. These silicate clouds form when the temperature and pressure reach precisely the right conditions for the evaporation and condensation of magnesium compounds. The interaction between these two cloud layers creates atmospheric dynamics that push the boundaries of planetary science. Webb's infrared observations revealed that both cloud layers are patchy and constantly changing, suggesting active weather patterns driven by the planet's rotation and internal heat sources. The iron clouds appear to follow different circulation patterns than the magnesium clouds, creating a complex three-dimensional atmospheric structure that varies greatly across the planet's surface. But the most puzzling aspect of this world's atmosphere are the regions above both cloud layers, where Webb discovered what the researchers call hotspots. These are regions of intense heat, apparently powered by radio auroras, electromagnetic phenomena similar to the aurora borealis on Earth, but operating at energy levels lethal to any known form of life. These auroras suggest that SIMP J0136 has an incredibly powerful magnetic field, far stronger than anything in our solar system. This magnetic field interacts with charged particles in interstellar space, creating electric currents that heat portions of the upper atmosphere to temperatures exceeding those in the metallic cloud layers below. Alison McCarthy, a graduate student leading the atmospheric analysis, described the planet as possessing mechanisms of variability that have been hypothesized but never directly observed. Complex interactions between iron clouds, magnesium clouds, and radio auroras create an atmospheric system that operates according to principles never before encountered. The existence of such complex atmospheric chemistry on a rogue planet raises troubling questions about planet formation and evolution. SIMP J0136 somehow developed and maintains this complex atmosphere while drifting through the cold void of interstellar space, far from any source of stellar energy. This suggests that rogue planets may be capable of supporting much more complex atmospheric processes than scientists previously thought. If a single rogue world can develop iron rain and magnesium clouds, then the galaxy could contain millions of such objects, each with unique atmospheric phenomena never before imagined. A world with metallic rain represents a new category of planetary atmosphere that challenges our understanding of the kinds of weather systems that can exist in the universe. A strange, cosmic owl-shaped galaxy is floating through deep space, revealing its tentacled structures, suggesting violent interactions never before seen. When James Webb captured images of what astronomers jokingly nicknamed the cosmic owl, they initially focused on its distinctive appearance. The galaxy's bright central region creates the illusion of two glowing eyes, while the surrounding gas and dust formations resemble the feathery outline of an owl's face. But detailed analysis revealed that this cosmic creature is far more alien and unsettling than its whimsical nickname suggests. The cosmic owl belongs to a class of objects called jellyfish galaxies, systems that appear to float through space with long tendrils of gas and stars trailing behind them. These tentacles aren't decorative elements, but rather evidence of the brutal tearing processes that rip apart the galaxy as it moves through its environment. The galaxy undergoes a process called gravitational pull, where its movement through the hot gas that fills galaxy clusters creates a cosmic headwind that literally blows away parts of the galaxy's structure. Imagine driving a convertible at high speed and having loosely packed luggage fly out of the back seat. The cosmic owl sheds parts of itself as it travels through space. Webb's infrared vision revealed the true scale of this cosmic violence. The galaxy's tentacles extend for hundreds of thousands of light years, containing billions of stars that have been torn from their former habitats. These stellar refugees now reside within the tentacles, isolated from the main body of the galaxy and slowly dissipating into the void. But the most disturbing aspect of the cosmic owl isn't what it loses, but what the process of torn-out stars reveals about galactic environments. The sheer pressure required to create such vast tentacles indicates that the galaxy is moving through an incredibly dense and hot environment, far more extreme than the relatively empty space between galaxies. This suggests that the cosmic web, the large-scale structure of matter connecting galaxies across the universe, is more violent and turbulent than scientists previously thought. Instead of galaxies moving peacefully through empty space, they are forced through environments that can literally tear them apart. This jellyfishing process also creates new opportunities for star formation within the tentacles themselves. As gas escapes from the galaxy and is compressed by the sheer pressure, it can trigger bursts of star formation in locations far from the main body of the galaxy. The cosmic owl simultaneously collapses and creates new stellar populations along its path. Webb's observations revealed active star-forming regions scattered throughout the galaxy's tentacles, glowing brightly with the blue light of young, massive stars. These stellar nurseries exist in gravitational isolation, billions of light years from the galaxy that originally provided them with their raw materials. The discovery of extensive jellyfish structures in Webb's deep images suggests that processes of galactic cannibalism and stripping are far more widespread than astronomers previously thought. The universe may be filled with cosmic refugees, stars and gas clouds torn from their parent galaxies and now drifting through the void. The cosmic owl represents just one example of the violence shaping galactic evolution on the largest scales. But even this galactic destruction pales in comparison to the stellar violence Webb discovered within individual star systems. Young stars create heavy elements that shouldn't yet exist, shaping a cosmic chemistry that challenges our understanding of stellar evolution. James Webb discovered young stellar systems producing heavy elements like oxygen, carbon, and nitrogen in quantities that should be impossible given their age. These stellar nurseries generate a complex chemistry that, according to all models of stellar evolution, requires billions of years to develop through successive generations of star formation and death. The mystery lies in metallicity, the astronomical term for elements heavier than hydrogen and helium. In the early universe, only these two lightest elements existed in significant quantities. All heavier elements, from carbon and oxygen to iron and gold, would have been forged in the nuclear furnaces of massive stars and dispersed into space when these stars exploded as supernovas. This process would take time. The first generation of stars, called population 3 stars, would have consisted almost entirely of hydrogen and helium. As they died, they enriched the surrounding space with newly formed heavy elements, allowing a second generation of stars to form with slightly more complex chemistry. This process of cosmic recycling continues for billions of years, gradually increasing the metallicity of star-forming regions. Webb discovered stellar systems that appear to have skipped several stages of this process. Young galaxies, formed when the universe was less than 1 billion years old, exhibit metallicity levels that would require several generations of stellar evolution. They produce oxygen, carbon, and nitrogen at rates inconsistent with their apparent age. The complexity of the early universe is astonishing. The galaxy JSGSC 131, observed just 330 million years after the Big Bang, displays bright hydrogen emission lines and traces of the formation of heavy elements. This indicates significant stellar evolution, challenging our understanding of the cosmic infancy. Unexplained chemistry is forcing scientists to reconsider fundamental assumptions about the formation of early stars. Either the first generation of stars was far more massive and short-lived than predicted by current models, allowing them to rapidly synthesize and disperse heavy elements, or unknown processes enrich the young universe with complex chemistry. The first hypothesis suggests that population 3 stars were cosmic monsters, possibly hundreds of times more massive than our Sun. These stellar giants burn through their nuclear fuel in a matter of millions of years before exploding as supernovas, scattering heavy elements across vast expanses. Such massive stars do not exist in the modern universe, but the extreme conditions of the early cosmos could have facilitated their formation. The second possibility is even more troubling. If unknown processes were responsible for the formation of heavy elements in the early universe, then our understanding of cosmic chemical evolution is fundamentally incomplete. A mechanism other than stellar nucleosynthesis may have dominated, creating complex chemistry through previously unimagined pathways. The rapid evolution of metallicity observed in the data also impacts our understanding of planet formation and the potential for life. If heavy elements became available much earlier than previously thought, rocky planets and the chemical building blocks of life may have emerged much earlier in cosmic history. These discoveries hint that the early universe possessed a chemical complexity that makes our models look like oversimplified approximations of reality. A planet orbiting our nearest stellar neighbor keeps appearing and disappearing in observations by the James Webb Space Telescope, and astronomers are baffled. In what researchers are calling the James Webb's most significant discovery to date, the telescope spotted a giant planet orbiting Alpha Centauri A, our nearest Sun-like star, only to lose sight of it entirely during subsequent observations. This cosmic disappearance stunt has given rise to one of the most baffling mysteries in exoplanet science. The planet, tentatively designated Alpha Centauri AB, appeared in Webb's initial observations as a thermal signature consistent with a world roughly the size of Neptune orbiting in the habitable zone of Alpha Centauri A. This discovery alone would have been revolutionary, representing the closest potentially habitable planet to Earth ever discovered. But when astronomers attempted to confirm the detection with additional observations, the planet simply wasn't there. Subsequent images showed no trace of the thermal signature so prominent in the original data. The planet had either moved to a position where Webb couldn't detect it, or had somehow ceased to exist. Several explanations have been proposed for this cosmic disappearance, each challenging the accepted understanding of planetary systems. The first hypothesis suggests that the planet has a highly elliptical orbit that takes it far from the star for most of the year, making it detectable only during brief periods, when it passes close enough to emit significant thermal radiation. However, orbital mechanics makes this explanation problematic. A planet with such an extreme orbit around Alpha Centauri A would be gravitationally unstable, likely ejected from the system by interactions with the star's binary companion, Alpha Centauri B. The gravitational dance between the two stars creates complex dynamic processes that make it difficult to maintain stable planetary orbits. The second explanation is even more troubling. The planet may be real, but surrounded by a variable dust cloud or debris ring that periodically obscures it from Webb's infrared sensors. This would mean the Alpha Centauri system is far more dynamic than previously thought, with constant collisions or disruptions creating temporary obscurations around the orbiting worlds. The third possibility challenges our understanding of planet formation. The thermal signature could represent a world still forming, accreting material from the protoplanetary disk in episodes that make it alternately visible and invisible to infrared observations. This would mean that planet formation is still actively occurring in the Alpha Centauri system, despite the stars being billions of years old. The most alarming explanation is that Webb has detected something that isn't a planet at all. The thermal signature could represent a previously unknown type of cosmic phenomenon, perhaps a dense cloud of warm debris, or even a failed star formation event occurring in the outer regions of the Alpha Centauri system. The mystery of the vanishing planet highlights how little we still know about planetary systems, even those in our immediate cosmic neighborhood. If a world can appear and disappear in observations of our nearest stellar neighbor, it raises questions about what other planetary phenomena might be hiding in plain sight. The vanishing planet Alpha Centauri serves as a reminder that the cosmos remains full of surprises that challenge our most basic understanding of how planetary systems work. Ancient magnetic fields detected throughout the cosmic web are as complex as the neural networks of the human brain, and they predate any known structure in the universe. The James Webb has discovered evidence of magnetic fields extending through the largest structures in the cosmos, creating patterns of connections that are eerily reminiscent of the neural networks found in the human brain. These pristine magnetic fields appear to be remnants of the first billion years of the universe's existence, when cosmic structure was still being formed through processes we barely understand. The discovery arose from Webb's observations of the cosmic web, a vast network of filaments and voids that organizes matter on the largest scales between galaxies and galaxy clusters. Thin streams of gas and dark matter create bridges spanning hundreds of millions of light years. Webb discovered that these cosmic filaments are threaded with magnetic fields of extraordinary complexity. The patterns of the magnetic fields reveal a level of organization that should not have existed in the early universe. Instead of simple, uniform fields, Webb discovered complex networks with nodes, connections, and hierarchical structures that mirror the topology of biological neural networks. The similarities are so striking that researchers are using the same mathematical tools developed to study brain activity to analyze cosmic magnetism. These ancient magnetic fields raise fundamental questions about cosmic evolution. Standard models suggest that magnetic fields in the cosmos evolve gradually as galaxies and stars form, with stellar winds and supernova explosions creating and strengthening magnetic structures over billions of years. The primordial fields detected by Webb appear to predate this process. The fields show evidence of influence on early galaxy formation in ways not accounted for by current theories. Magnetic pressure and magnetic reconnection events may have shaped the collapse of gas into the first stars, influencing stellar masses, formation rates, and the chemical evolution of early galaxies. Perhaps most troubling, these magnetic networks suggest the nature of cosmic structure formation. Brain-like patterns indicate that the universe developed organizational complexity much earlier than scientists previously thought. Instead of simple gravitational collapse creating cosmic structure, the early universe may have functioned more like a gigantic information processing system. Magnetic field networks also appear dynamic, with connections forming and breaking over cosmic time. Webb has discovered evidence of magnetic storms engulfing entire galaxy clusters, events that could influence star formation and galactic evolution on a vast scale. This discovery has implications for our understanding of dark matter and dark energy. Magnetic fields can interact with charged particles in ways that influence how matter clumps on large scales. If primordial magnetism was more complex and powerful than current models suggest, this could explain some of the discrepancies Webb has uncovered in the formation of cosmic structure. Brain-like magnetic networks pose a fundamental challenge to our understanding of how complexity arises in the universe. If such complex organizational structures existed in the early days of the cosmic web, it suggests that the universe possesses intrinsic tendencies toward complexity that we have never recognized. These primordial magnetic fields may be evidence that the universe itself possesses properties similar to living systems, with information processing and organizational capabilities arising from physical processes we do not yet understand. The supermassive black hole at the center of our galaxy pulsates with irregular rhythms, indicating unknown physics operating at the edge of spacetime. Sagittarius A*, a 4 million solar mass black hole at the center of the Milky Way, has quietly puzzled astronomers for decades. But continuous monitoring by the James Webb Space Telescope has revealed something unprecedented. The cosmic monster exhibits chaotic brightness fluctuations, reminiscent of a heartbeat with no discernible pattern. Using Webb's near-infrared camera, researchers observed Sagittarius A* for 48 hours, spread across several sessions over the course of a year. What they discovered is a black hole in constant flux, with its accretion disk producing a continuous but chaotic series of brightness variations, punctuated by sudden, dramatic outbursts. Observations revealed constantly changing, pulsating brightness in the region of the black hole's event horizon. Then, without warning, enormous streams of radiation suddenly erupted from the accretion disk before quieting down again. These outbursts appear completely random, defying all attempts to find underlying patterns or periodicities. Farid Yousafzard, a professor at Northwestern University who led the study, described this behavior as unlike anything previously observed in supermassive black holes. The team found no pattern in the activity, suggesting that the processes driving these brightness variations operate according to physics that current models don't fully capture. Two mechanisms appear to be driving this cosmic heartbeat. Short-term fluctuations likely result from turbulence in the accretion disk, where magnetic field interactions compress the plasma and create temporary bursts of radiation. Think of it as cosmic lightning, occurring in superheated gas spiraling toward the black hole's event horizon. But larger bursts suggest something more dramatic. These massive increases in brightness may be the result of entire chunks of matter crossing the black hole's photon ball, the region where light itself begins to orbit the black hole before either escaping or falling beyond the event horizon forever. The irregular nature of these events suggests that Sagittarius A* is more active than astronomers previously assumed. Instead of the relatively quiet, slowly feeding monster described in textbooks, the Milky Way's central black hole appears to be in a state of constant, low-level violence, gobbling up matter in unpredictable bursts. What makes this behavior truly alarming is its implications for the physics of black holes near the event horizon. The brightness fluctuations arise from regions where space and time are strongly distorted by gravity, creating conditions in which matter and energy behave according to principles that push general relativity to its limits. The chaotic nature of the brightness variations suggests that quantum effects may play a role in black hole accretion processes. Near the event horizon, the boundary between classical and quantum physics becomes blurred, potentially creating phenomena that exist nowhere else in the universe. The heartbeat also raises questions about what happens to the information falling into black holes. If the behavior of the accretion disk is truly random, it could indicate that black holes destroy information in a way that violates the fundamental principles of quantum mechanics. The irregular pulsations of Sagittarius A* represent our closest glimpse into the physics operating under the extreme conditions that the universe can create, where gravity becomes so strong that space and time themselves begin to disintegrate. Invisible forces are rebuilding the cosmic structure through violent processes that leave galaxies torn apart and scattered across millions of light years. The James Webb Space Telescope has discovered evidence that dark matter, the mysterious substance that makes up 85% of all matter in the universe, is involved in violent interactions that can destroy entire galaxies and alter the cosmic structure on the largest scales. These dark matter catastrophes operate through mechanisms that remain completely invisible, except for their devastating effects on ordinary matter. Evidence comes from Webb's observations of galaxy clusters, regions where hundreds of galaxies are held together by the gravitational influence of massive concentrations of dark matter. When these cosmic cities collide, they create some of the most energetic events in the universe, releasing energy comparable to billions of supernova explosions. But Webb's detailed images have revealed that the violence extends far beyond the visible collision zones. Galaxies located millions of light-years away from cluster collisions show signs of being violently disrupted by gravitational forces that can only be explained by dark matter interactions operating on previously unimaginable scales. The telescope has discovered vast streams of stars and gas connecting galaxies across vast distances, creating bridge-like structures spanning the space between individual galactic systems. These stellar streams are the torn remnants of galaxies that were gravitationally torn apart by dark matter during cluster collisions. What makes this cosmic violence particularly disturbing is its hidden nature. While interactions of ordinary matter create visible fireworks through electromagnetic radiation, dark matter collisions produce no light, heat, or electromagnetic signatures. The only evidence of these cataclysmic events is their gravitational effects on visible matter. Webb's infrared sensitivity revealed the full scale of this dark violence. Faint stellar streams and tidal tails extend for millions of light-years around galaxy clusters, creating vast webs of disrupted matter that previous telescopes were too insensitive to detect. Each stream represents a galaxy that has been partially or completely destroyed by dark matter interactions. The scale of this destruction suggests that dark matter does not simply provide a passive gravitational framework for the cosmic structure. Instead, it actively participates in the restructuring of the universe through violent processes that can eject galaxies from their parent clusters, strip away their gas reserves, and disperse their stars into intergalactic space. Computer simulations of dark matter interactions suggest that these violent events may be fundamental to cosmic evolution. Dark matter particles can undergo collisions and gravitational interactions that create shock waves that propagate through the cosmic web, influencing galaxy formation across vast regions of space. Perhaps most troubling is what this hidden violence suggests about the nature of dark matter itself. If dark matter can participate in such energetic interactions, it may possess properties beyond simple gravitational attraction. Some models suggest that dark matter particles may undergo phase transitions or interact through forces we have not yet identified. The discovery of the ubiquitous violence of dark matter also impacts our understanding of galaxy evolution and the formation of cosmic structure. If galaxies are continually disrupted and reformed by dark matter interactions, the universe may be far more dynamic and chaotic than our models predict. These invisible catastrophes represent a fundamental aspect of cosmic evolution, operating entirely beyond our direct observation, shaping the universe through violence we can detect only in its aftermath. A distant galaxy warps spacetime so dramatically that it appears in multiple places simultaneously, creating gravitational effects that challenge our understanding of general relativity. The James Webb has discovered a galaxy so massive and dense that its gravitational field creates multiple images of it in the cosmic sky, each showing the same star system at different stages of its evolution. This extreme gravitational lensing effect demonstrates the curvature of spacetime, operating at levels that push Einstein's general theory of relativity to its theoretical limits. The phenomenon, called strong gravitational lensing, occurs when an object becomes so massive that its gravity bends the fabric of spacetime, like a cosmic magnifying lens. Light from more distant objects follows these curved paths, creating distorted or multiple images that can appear in unexpected places across the sky. But this particular galaxy creates lensing effects far more extreme than anything observed before. Webb discovered at least 4 separate images of the same background galaxy, each magnified to varying degrees, and showing the stellar system at different epochs in its history. The gravitational field is so powerful that light takes different amounts of time to travel along each curved path. This time lag effect means astronomers are essentially observing the history of the same galaxy unfolding in multiple versions simultaneously. One image shows the galaxy as it was 800 million years ago, while another shows its structure a billion years in the past. A lensing galaxy has created a cosmic time machine that reveals the evolution of stars across multiple epochs. What makes this discovery truly troubling is the proposed mass distribution in the lensing galaxy, which is necessary to create such extreme spacetime curvature. The galaxy must contain concentrations of dark matter much denser than current models predict. The dark matter appears to be clustered into structures that challenge our understanding of how these mysterious particles interact and organize. The lensing effects also reveal a substructure in the dark matter distribution that should not exist according to standard cosmological models. Instead of smooth dark matter halos surrounding the galaxy, Webb discovered evidence of dark matter clumps and voids, suggesting complex internal dynamics operating through unknown mechanisms. Measurements of the time delay between different lensed images provide direct observational evidence of spacetime curvature acting in accordance with the predictions of general relativity. But the extreme nature of lensing pushes these effects into regimes where quantum gravitational effects can begin to influence the classical geometry of spacetime. Perhaps most troubling, this discovery suggests the prevalence of such extreme gravitational environments in the universe. If a single galaxy can create such a strong curvature of spacetime, it's possible that there are many other cosmic regions where space and time are distorted beyond our current ability to model or understand. The multiple images also reveal that the lensed galaxy itself is undergoing rapid evolution, with varying rates of star formation between different time periods visible in each image. This opens unprecedented opportunities for understanding the evolution of galaxies during their most turbulent stages. Time-warped galaxies are natural laboratories for studying general relativity under extreme conditions, demonstrating how massive objects can literally alter the geometry of space and time around them. These gravitational effects manifest themselves at scales where classical physics begins to break down, potentially revealing new aspects of cosmic structure that exist at the boundary between general relativity and quantum mechanics. Stars across the universe devour their companions in such frenzied feedings that they give rise to entirely new types of cosmic explosions. The James Webb Space Telescope has obtained direct evidence of stellar cannibalism occurring throughout the universe, suggesting that binary star systems often culminate in catastrophic episodes in which one star literally devours its companion. These cosmic feedings produce some of the most powerful explosions in the universe, generating energies capable of outshining entire galaxies. The process begins when the two stars orbit each other close enough for their outer atmospheres to interact. The more massive star gradually strips its companion, creating streams of superheated gas that spiral inward, forming bright accretion disks. What begins as a gradual, eating process can suddenly accelerate, turning into a catastrophic engulfment event. Webb's infrared vision has allowed us to see these stellar feedings in unprecedented detail. The telescope can penetrate the gas and dust that typically obscure such violent events, revealing how matter flows from the victim stars to their companions in complex gravitational dances that culminate in cosmic cannibalism. The most extreme cases involve white dwarfs, dense remnants of dead stars roughly the size of Earth, but containing the mass of our solar system. When these cosmic vampires accrete matter from companion stars, they can trigger thermonuclear explosions called Type Ia supernovae, which temporarily outshine billions of ordinary stars. However, Webb has detected even more violent cases of stellar cannibalism involving neutron stars and black holes. When these ultradense objects consume companion stars, they generate kilonova explosions that create heavy elements like gold and platinum, simultaneously emitting gamma-ray bursts detectable for billions of light-years. The telescope has documented the entire life cycle of stellar cannibalism, from the initial stages, when companion stars begin to lose matter, to rapid accretion phases, when feeding accelerates dramatically, and to final explosive events that disperse heavy elements across the cosmos. Perhaps most alarming is how widespread these cosmic feedings appear to be. Webb surveys suggest that stellar cannibalism may be a fundamental driver of chemical evolution in the universe, responsible for the creation and distribution of many of the heavy elements necessary for the formation of planets and, potentially, life. The violent nature of these events also impacts the surrounding stellar nurseries. Explosions of stellar cannibalism can trigger or halt star formation across vast regions, creating feedback loops that influence galaxy evolution on scales far larger than the original binary systems. Webb also found evidence of failed cannibalism, where binary systems began the feeding process but collapsed before reaching their explosive conclusions. These cosmic near collisions produce exotic stellar remnants with properties unlike anything in our galactic neighborhood. The prevalence of stellar cannibalism is forcing astronomers to reconsider how binary star evolution influences cosmic chemical evolution. Instead of stars leading isolated lives and peacefully dying, many engage in turbulent, feeding relationships that culminate in catastrophic explosions. These cosmic feedings are one of the primary mechanisms by which the universe creates and distributes the heavy elements necessary for complex chemistry and, potentially, life itself. Evidence is accumulating that reality itself is beginning to unravel on a cosmic scale, revealing fundamental cracks in the fabric of space-time that challenge our most basic understanding of physics. The James Webb's most troubling discovery may not be any single object, but rather the accumulated evidence that space-time itself becomes unstable under extreme conditions found throughout the universe. The telescope has detected gravitational anomalies, unexplained energy signatures, and structural irregularities that suggest the smooth fabric of spacetime described by general relativity is more fragile than anyone imagined. This evidence comes from multiple sources throughout Webb's surveys. Gravitational lensing effects around some massive objects defy the precise predictions of general relativity, displaying small but persistent deviations that may indicate a breakdown of the structure of spacetime under extreme gravitational stress. These anomalies appear near black holes, in the cores of galaxy clusters, and around other massive cosmic structures. Quantum mechanics predicts that spacetime on the smallest scale should be foamy and chaotic, with virtual particles and energy fluctuations creating a turbulent quantum foam underlying smooth classical geometry. But Webb observations suggest that this quantum foam can float, to macroscopic scales under certain extreme conditions. The telescope has detected unexplained energetic emissions from regions where quantum effects should not be observed, including mysterious radiation signatures from the event horizons of black holes and anomalous heating in the cores of galaxy clusters. These phenomena may represent quantum foam breaking through into classical spacetime during particularly violent cosmic events. Perhaps most disturbing are Webb's observations of what astronomers call cosmic strings, hypothetical one-dimensional defects in spacetime that may have formed during the earliest moments of the universe. If these structures exist, they represent fundamental cracks in reality itself, places where spacetime is literally torn or folded in ways that disrupt our understanding of cosmic geometry. The telescope has identified several candidate cosmic string signatures, including gravitational lensing patterns, that cannot be explained by any known distribution of matter or energy. These observations suggest that the universe may contain scars from its violent birth, defects that linger as vulnerabilities in the fabric of spacetime. Webb also found evidence of vacuum decay events, regions where the quantum vacuum appears to have decayed to lower energy states through processes that release enormous amounts of energy. These events may represent fundamental phase transitions in the fabric of reality itself. Accumulating evidence suggests that the universe operates closer to the edge of physical stability than previously thought, under extreme conditions associated with massive gravitational fields, high energy density, or exotic states of matter. The fundamental structure of spacetime can become unstable. These breakthroughs in quantum foam have profound implications for our understanding of cosmic evolution and the ultimate fate of the universe. If spacetime can become unstable under conditions that naturally exist in the cosmos, this raises questions about whether reality itself might be more temporary and fragile than we imagine. The discovery of quantum effects operating on cosmic scales also suggests that the boundary between quantum mechanics and general relativity may be more permeable than theoretical physics predicts, with implications for our understanding of black holes, cosmology, and the fundamental nature of reality. The coordinated rotation of galaxies and the strange behavior of cosmic expansion suggest that we may be living inside a black hole within the larger universe. The most terrifying possibility raised by the James Webb discoveries is that we are inside a massive black hole existing within a larger cosmic structure. This theory of black hole cosmology explains several of Webb's most puzzling observations, including the coordinated rotation of galaxies and the expansion rate discrepancies that have shattered conventional cosmology. The evidence begins with the rotation patterns of galaxies that Webb discovered during its deep surveys. Galaxies separated by millions of light-years rotate in coordinated directions, a phenomenon that should be impossible unless the entire universe has a preferred rotation axis. In black hole cosmology, this coordination would result from our universe inheriting the angular momentum of the parent black hole that contains us. The theory suggests that what we call the Big Bang was actually our universe crossing the event horizon of a massive black hole in a higher dimensional space. From our perspective inside the black hole, this crossing appears as cosmic expansion. But from the perspective of the larger universe, we are falling toward the black hole's singularity in a process that takes infinite time due to gravitational time dilation. This scenario explains the accelerated expansion of space that we attribute to dark energy. As we travel deeper into the parent black hole, the curvature of spacetime increases, creating the illusion of accelerated expansion when we are actually approaching regions of stronger gravitational distortion. Webb's discovery of primordial black holes that predate star formation also fits the black hole cosmology model. These ancient monsters could have been smaller black holes that existed in the parent universe before we crossed the event horizon, emerging in our cosmic history as primordial objects formed before ordinary matter could collapse into stars. The coordinated rotations of galaxies that Webb observed over vast regions of space make perfect sense if our universe inherited angular momentum from a rotating parent black hole. Galaxies don't mysteriously coordinate their motions. They all share the same cosmic rotation, which was imprinted on spacetime during the formation of our universe. Even the discrepancies in the expansion rate that have puzzled astronomers fit into the model of black hole cosmology. Different measurement methods can detect different aspects of our motion through the curved spacetime inside the parent black hole, creating apparent contradictions arising from viewing the same phenomenon from multiple perspectives. If black hole cosmology is correct, it means that everything we can observe, from the cosmic microwave background to the most distant galaxies, exists within the event horizon of an incomprehensibly massive black hole. We would be forever separated from the larger universe that contains us, unable to communicate with or influence anything outside our cosmic prison. The theory also suggests that black holes throughout our universe could contain entire universes themselves, creating a nested hierarchy of cosmic structures, with each black hole serving as a gateway to a complete cosmic world with its own physics, evolution, and, potentially, life. This possibility transforms our understanding of cosmic meaning and our place in the broader fabric of reality, suggesting that what we call the universe may be just one bubble in an infinite multiverse of black hole universes. The discoveries made by the James Webb do more than simply challenge our understanding of the cosmos. They fundamentally change what it means to be human in a universe far stranger and more dangerous than we ever imagined. Every assumption we had about our cosmic environment has been shattered by Webb's revelations. We thought we understood how galaxies form, how black holes grow, and how the universe expands. Instead, we discovered that space is filled with impossible objects, wild processes, and phenomena that operate according to physical laws we don't understand. The universe Webb reveals is not the orderly, predictable cosmos described in textbooks. It is a realm where galaxies can form faster than physics allows, where black holes roam naked through space, and where the very fabric of spacetime can be unstable. We live not in a cosmic garden designed for life, but in a turbulent arena where reality itself can collapse under extreme conditions. Perhaps most alarmingly, these discoveries suggest our cosmic isolation. If we live inside a black hole universe, as evidence increasingly suggests, then we are forever cut off from any larger reality that contains us. Every signal we send, every exploration we undertake, will remain locked within our cosmic prison. The prevalence of cosmic violence discovered by Webb also affects our long-term survival prospects. The universe is filled with wandering black holes, rogue planets broadcasting mysterious signals, and stellar cannibalism events that could sterilize entire regions of space. Our galactic neighborhood may be far more dangerous than we thought. The rapid pace of discovery has also revealed how little we truly know about the cosmos we inhabit. Despite centuries of astronomical progress, Webb's first few years of operation have uncovered phenomena that require a complete rewrite of our understanding of cosmic evolution. If we were so wrong about fundamental cosmic processes, what else might we have missed? The telescope's discoveries about early galaxy formation and primordial black holes suggest that the universe achieved complexity much earlier than we thought possible. This means that cosmic evolution may follow paths we've never considered, potentially including the development of intelligence and civilization on timescales and in environments we'd never imagined. But Webb's revelations also offer hope. The universe's capacity to surprise and reveal complexity suggests that cosmic evolution may be far richer and more diverse than our models predict. If reality can produce impossible galaxies and naked black holes, it may also create life and intelligence that operate according to principles we've yet to discover. The telescope has effectively revealed that we are cosmic infants, living in a universe that operates by rules we are only beginning to comprehend. Every strange object Webb discovers, every impossible phenomenon it uncovers, represents an opportunity to expand our understanding of what is possible in a cosmos that clearly enjoys defying our expectations. Perhaps most importantly, Webb's discoveries remind us that the universe doesn't have to be understandable. Reality operates according to its own logic, following principles that may be fundamentally alien to human intuition. Our survival and success as a species depend on our ability to adapt our understanding to match the cosmos as it actually is, not as we wish it to be. The universe revealed by the James Webb is strange, turbulent, and often incomprehensible. But it is also the only reality we have. And understanding it, however unsettling that understanding may be, represents our best hope for navigating the cosmic future that awaits us.